All right. So by the end of this lesson, you'll be able to describe what inertia is and how it plays a role in motion, to determine the direction of acceleration by the net force, motion of the object, and a velocity versus time graph. Okay. So here we go. So I don't know if you've ever seen someone do this, or maybe you did this, but like you go to a bowling alley and you're like, check this out. Slow roller. Okay. Okay. How theoretically, how would you describe how that bowling ball is rolling as it goes down the bowling lane? Thanks, sir.
Decelerating.
Theoretically.
In the positive direction.
Bless you. Theoretically, kind of keeps rolling.
It's just rolling.
Constant speed. So just
What if it changes direction?
Just a little bit. Oh yeah. So we're assuming like a really slippery level floor. Okay. Have you ever tried to walk on a bowling lane before? Real slippery. Like past the line, it's like kind of rough. Okay. So the bowling ball doesn't have much friction. Okay, I want you to pretend or remember the last time you were in outer space and you threw a ball. You remember that? When you threw it and we were like way away from any type of planets, and you threw it, how did it move? Constant speed, straight line path, forever and ever. No fill-ups required. It just continues to go. Okay. You all have heard about Newton's first law. An object at rest will stay at rest. An object in motion will stay in motion unless acted on by an outside force. Okay. We are solid with the whole an object at rest will stay at rest. That happens all the time, all over the place. But an object in motion wants to stay in motion. Well, that rarely happens here on Earth. When I push something, when I push this ball, eventually this thing's going to like slow down and stop, right? Why? Friction, gravity, air resistance. All three of those are examples of a what?
Outside force.
An outside force. Okay? That messes with stuff. If you get rid of all of that, an object in motion is going to continue to move at a constant speed, a straight line path forever and ever and ever. Why? Because that's what it wants to do. That's its inertia. Its natural tendency is like, yes, I'm moving. I want to stay moving. That's why air hockey tables are so cool. The air gets rid of the friction. There is some air resistance, but like it takes care of the friction. It just floats on the. Like, whoa, that's so cool. Because we got rid of friction. You good with that? Okay. So, thank you. An object in motion wants to continue moving in a constant speed in a straight line path forever and ever and ever and ever and ever. It does not run out of energy. It does not need a fill up. It does not, like all those things that we think happen here on Earth, it just keeps on going. Its natural state is like, yes, I'm moving. I want to keep on moving. Good with that? Okay. Okay. I have a fan cart here. Okay. I turn it on. Okay. For this way. Which way is the cart being pushed by the fan? Not which way the fan is pushing air, but which way the cart is being pushed. There we go. All right with that? That is the direction of the net or the total force. Okay. That is also the direction of acceleration. You okay with that? Okay. We are going in the positive direction. And speeding up. If we're speeding up, then the sign of acceleration is going to be what compared to the sign of velocity? The same. Good with that? If we're moving this way, if we're moving this way, and we're slowing down, what's the sign of acceleration? Positive. Video would help. Okay. Which way is the direction of the force acting on the cart in this example? This way. The direction of the net force, the total force, will always be in the same direction as acceleration. Okay? Good with that? Do not associate speeding up with a positive acceleration or slowing down with a negative acceleration. This is why I hate the word decelerate, because that gets people all confuzzled. Okay? Do not associate speeding up with a positive acceleration. Do not associate slowing down with a negative acceleration. Okay.
So if my car, let's say I'm going like 60,
Yep.
I throw it in neutral.
Yep.
Okay. And then I hit the brakes.
Yep.
Am I accelerating in the other direction?
You're experiencing accelerate. The way I would verbalize it is, you're experiencing acceleration in the opposite direction you're moving.
Okay.
You could say you are slowing down as you move that way. You're accelerating. I would not say accelerating.
So my brakes are the acting force in this situation?
Yep.
Okay. So it would be the same if you put it in reverse. And then just be more force in the opposite direction.
We'll talk. We will actually have that question come up probably in like 3-4 weeks. It's a good question. Okay, good with that. So, the direction of the net force of the total force will always be in the same direction as acceleration. The direction of the total force will always be in the same direction as the acceleration. We're not going to use this equation yet. It'll come. But does mass have direction? Does mass have direction? No, it's just a thing. Okay. Does acceleration have direction? Yes. So it's a vector quantity. We denote that with that. Does force have direction? Yep. So mathematically, the direction of the net force has to be the same direction as acceleration because mass doesn't have direction. Does that make sense? Okay. So that's the math reason. Conceptually, this is true because the net force, the total force, causes acceleration. And this is why I brought up this idea of inertia. If you're moving, the object naturally just wants to stay moving, like, yes, at a constant velocity. But if your velocity changes, that's acceleration, right? What would cause the velocity to change? Something acting on a force. So if I'm moving along like this, and then I speed up, something has to act on me to get me going. Okay? If I'm moving like this, and then I'm slowing down, something has to act on me to make me slow down. Good with that? Okay. Stow those phones, John. Tell your neighbor.
Oh, yeah.
Doesn't sound smart when I say it, but I know what it is. I know what it is.
Correct answer is? Correct answer is B. You're moving in the positive direction, slowing down, therefore the sign of acceleration has to be what compared to the velocity? Has to be in the opposite direction of velocity, so negative. Okay? You're moving in the positive direction. What's the direction of the force that would have to cause you to slow down? In the opposite direction of motion. In the negative direction, that's the direction of the net force, the total force. Therefore, the sign of acceleration is also negative. Two different ways to describe the motion, or describe the acceleration. Try that one. Thumbs up when you have a guess. Talk to your neighbor.
Speeds up, and it goes faster and faster and faster until he gets the zooms pretty fast. The zoomies, yeah. You know how your dog gets the zoomies?
Correct answer is B. Okay. You're speeding up in the negative direction. Okay. Therefore, the sign of acceleration has to be the same as velocity. You're speeding up. You're moving in the negative direction. What would cause you to speed up? What force? In the same direction as the way you're moving. Negative acceleration. Good? Bless you. All right. So we've talked about it. Look at the direction of the net force. Or if you're speeding up, it has the same sign as velocity. If you're slowing down, the acceleration has the opposite sign of velocity. Good with that? It's kind of a summation of all that. Bless you. Tell your neighbor.
Oh, it's decelerating. It's not deceleration.
The force fell again. Just how Warner Brothers is going in the positive, trying to go in the positive direction.
Correct answer is A. Feeling pretty good about this? Okay. All right, check this out. So, after I let go of it, don't look at the pushing part. What's the sign of acceleration? We'll say right, left. Which way is the acceleration? Left. Which way is the direction of acceleration? Right or left? Still to the left. If I put it together, that was experiencing constant acceleration to the left the entire time. So if something experiences acceleration in the opposite direction of motion for long enough, at some point it's going to stop, turn around, and speed back up in the same direction as acceleration. Good with that?
Yes.
Okay. Give that one a shot. Thumbs up if you got something. Talk to your neighbor.
He initially has this positive, and then Negative all within 1 second. What was the slowest acceleration? Oh wait, no, that would be okay, sorry. Because A is
Correct answer.
he
He just does. He's just
because positive 3, negative 3. Wait, no. One of them might go to negative. My brain's not really concentrating. Okay? My brain is.
Correct answer is
Oh my god.
Hey, who said B?
Give me a
Who said do something?
all right. Here we go. Here's the math point of view. So final minus initial velocity over time duration. Okay, final velocity was a negative 3 meters per second. Initial velocity was a positive 3 meters per second. Over 1 second, you get negative 6 meters per second squared. Does that make sense? Okay. Conceptually, here's the idea. The squirrel is initially going in the positive direction, and it's going to slow down. So if you're slowing down in the positive direction, what's the sign of acceleration? Negative. Stops, turns around, and now speeds back up in the negative direction. Therefore, the sign of acceleration is still negative. Good? Sorry, real quick. The math and the concept should always go hand in hand. Always. If they don't, something's wrong. Okay? I really like this question. Do not influence or be influenced until I tell you to converse. Thumbs up when you have a guess. Have a conversation.
Okay. So, okay, they could both be going the same, they could both be going the same speed, one can accelerate. Because these balance. Okay, not necessarily, because they will be going in opposite directions. One, they can both be accelerating. So where's the, okay, so not enough information. Okay, not enough information, but where is that? That's E. Okay, well, it's, yeah. You don't have enough information. Because they could be both, yes, going in the same direction. It could be going opposite directions. There's not a specification.
Music.
If they said, if they were, if they said that they were going in the same direction, what yeah. What did you say initially?
Correct answer is? Well done. Educated elephants. Okay. So, knowing the direction of acceleration by itself does not tell you much. The only thing you know is the rate of change of velocity is greater for the stallion than the mare. The only other thing you know is the direction of the net force. The net force on the stallion is going in the negative direction. The net force on the mare is going in the positive direction. That is all you know. Okay. Could they be going in opposite directions? Sure. Do they have to be? No. I could be going in the positive direction and experience a negative acceleration and be slowing down. I could be going in the positive direction and experiencing a positive acceleration and speeding up. I could be going in the negative direction and experience a negative acceleration and speed up. I could be going in the negative direction and experience a positive acceleration and be slowing down. Lots of options. I would need to give you some more details for you to come up with any conclusions. Good with that? All right. Have a conversation. Tell them why you think so.
But
Your acceleration graph will always be over.
why can't it be? Well, yeah, being will ever. There's a chance that
The
it's
green
deep
is an acceleration graph, which means
because going forwards with the force of motion detector. Oh, I know. Then that could be deep. But for the velocity, it's the negative direction. It's starting fast. And it's starting my brain hurts looking at this.
Correct answer is okay. The fastest, in my opinion, the fastest way to look at this is the slope of a velocity versus time graph tells us the value of acceleration. How would you describe this slope? Is this a positive or negative slope? Is a positive slope. Positive slope. And it's a constant value. In this class, velocity versus time graphs will all be straight lines. So the slope is going to be constant. Therefore, the value of acceleration is going to be a positive constant value. Okay? Here's the story. You start fast in the negative direction, and you end up slow in the negative direction. You're slowing down in the negative direction. Therefore, the direction of acceleration is positive in the opposite direction of velocity. We have negative velocity is slowing down with a positive acceleration. You need to be able to think of both ways. Okay? Try that one. Thumbs up when you have a guess. These lines are parallel. Have a conversation.
See, it's not the same slope, it's just like different directions. One is just slowing down, one is speeding up. So it would be the same.
Parallel, they have the same slope. Okay, are we talking about the magnitude of the acceleration or just the
Yep, it's C.
acceleration?
Everything.
Okay.
Magnitude and direction.
So it doesn't matter positive or negative, you just want to know which one's greater.
No, it does.
It doesn't matter whether
going in the negative direction.
Okay, so
I got something for the class.
okay.
Yeah, one's in the negative, so one's got a higher acceleration. He's just said everything, it's not about magnitude,
So
one other
both
thing
negative,
together.
and they're parallel lines, so they have the same slope. So it's C.
Yeah, but you don't know if they keep going from there, they might stop at that ending point. They're both in the negative direction, so yeah, they're both in the negative direction, but one is green and stops at 0. One
Okay, correct answer is okay. Correct answer is C. Okay, here we go. In math class, do you care which quadrant they go through to figure out the slope? No, you could pick a point here and a point there and like rise or run. Okay, it does not matter where it falls on the graph to figure out the slope. Okay, the story between each of these have parallel slopes, therefore they have parallel accelerations. The story is this starts fast in the positive direction and slows down, meaning you have a negative acceleration. This starts slow in the negative direction and speeds up in the negative direction. Therefore, this also has a negative acceleration. How are we doing? Okay, learning? I'd capture that. Whatever you capture, I would like. Okay, so if you are speeding up, then the sign of acceleration is the same as velocity. So here we're in negative land. You have a negative acceleration. If you're slowing down, then the sign of acceleration is the opposite of velocity. Here we have a positive velocity, therefore you have a negative acceleration. Good with that? Next question. I want to make sure everybody's on the physics train. You're welcome. Thumbs up when you have a guess. Have a conversation.
Start out. Then stop.
So why would the acceleration stay a certain one?
So you're starting positive. That's starting with the negative.
I think so.
Oh, yeah, it's so fast. I
Correct answer is okay. Two different ways to look at it. The slope. How would you describe the slope of that line? Constant negative. Constant negative value. The story to produce this. You start in the positive direction moving fast. Now your positive direction moving slow. So you're slowing down in the positive direction. So you have a positive or negative acceleration. Negative acceleration. You stop, turn around, you're moving slow in the negative direction. Now you're moving fast in the negative direction. So you're speeding up in the negative direction. So that means you have a negative or positive acceleration. You have a negative acceleration. Now, someone in the first hour asked an excellent question. They're like, why at this turnaround point is there still acceleration? Why wouldn't the graph look like that? Like have a little hiccup? Yep, worksheet. Okay, so does that make sense to their question? Like you stopped and turn around. Why do we still have acceleration there? How long is the velocity zero? Just a moment, an instant. The moment right beforehand, were they moving? Yes. The moment right afterwards, were they moving? Yes. Was velocity changing from moment to moment to moment? Yes. It doesn't, like it's just zero for just a moment. Just there. Does that make sense? Okay. And so you have acceleration the entire time. No hiccups. Good with that? Last question. Tell your neighbor. Tell them why. Correct answer is? C is correct. You have a steeper slope, positive, than you do the negative slope. Good? Got a worksheet due tomorrow over this stuff.